Question 10 on the math subject GRE practice test is a pretty fun little problem. We're asked about the power series expansion of this function 1 over 1 minus x squared. For the sake of notation, maybe I'll call that thing f of x. And then our power series over here, since it's going to be a polynomial, maybe I'll call that p of x. And while this summation notation is really helpful, it might help people to see what's going on if I wrote out the first few terms of this infinite sum. So if I change all the n's into zeros, I got a0 x to the 0 power. If I change all the n's into ones, I got a1 x to the first power. If I change all the x's into twos, I got a2x squared. Change them into threes, I got a3x cubed, and so on. What Taylor series allow us to do are write formulas for each of these different coefficients. So something you may or may not have memorized coming into this test is that a0 is always going to be f of 0. That's assuming our power series is centered at 0, which I think makes it a Maclaurin series. Or maybe a Maclaurin series that's centered at 0 is a Taylor series. I never remember. Whatever. Anyways, we know this power series is centered at 0 because the general form of a power series is the sum from n equals 0 to infinity of a n x minus c to the n power. C is where this series is centered. And as you can see down here, we just have x to the n power, so c must be equal to 0. Anyways, the first coefficient, a0, is always equal to f of 0. The second coefficient, a1, is always equal to f prime of 0. The third coefficient, a2, is always 1/2 f double prime of 0. The next Taylor series coefficient, a3, is always 1/6 f triple prime of 0. That's more than we need for this problem, but in the interest of really making this pattern explicit, you can think about this as f of 0 divided by 0 factorial, and this is the first derivative of f evaluated at 0 divided by 1 factorial. This is the second derivative of f evaluated at 0 divided by 2 factorial. This is the third derivative of f evaluated at 0 divided by 3 factorial. You get the point. An would be equal to the nth derivative of f evaluated at 0 divided by n factorial. If you have this memorized coming into the test, answering this question is as easy as plugging numbers into these first three formulas. Looking at these formulas, it looks like I need f of 0, f prime of 0, and f double prime of 0. So maybe I should take some derivatives here. Before I go taking any derivatives, I should fix f of x here. I forgot to set a parentheses. That's really important. It's the entire denominator that's being squared. Anyways, now I can take some derivatives. If you're really comfortable with calculus, you might be able to take the derivative the way this is written. But if you're worried you make a little mistake, it might help to rewrite this as 1 minus x to the negative 2 power. Written in this form, f prime of x would be equal to, let's see, I bring the negative 2 down in front, and then I got 1 minus x to the negative third power using the power rule. But then be careful, you're not done. You still got to take the derivative of the inside part here. That's a chain rule. The derivative of 1 minus x is negative 1. If I clean things up a little bit here, negative 2 times negative 1 gives me a positive 2. So I got 2 times 1 minus x to the negative third power. In other words, 2 over 1 minus x cubed. I got my first derivative. I'm also going to need the second derivative. That's just the derivative of the derivative. Use whichever of these forms you like the best. I kind of like this one the best. If I take the derivative of this form, I leave the 2 alone, bring the negative 3 down in front. That gives me negative 6 times 1 minus x to the negative fourth power. But again, I'm not done. I have to multiply by the derivative of the inside function, which gives me another negative 1. The second derivative of x is just equal to 6 times 1 minus x to the negative fourth power. In other words, 6 over 1 minus x to the fourth. For a0, all I got to do is evaluate f of 0. F of x is 1 over 1 minus x squared. So f of 0 would be equal to 1 over 1 minus 0 squared. In other words, 1 over 1. In other words, 1. a1 is just equal to f prime of 0. F prime of x up here is 2 over 1 minus x cubed. So f prime of 0 would be 2 over 1 minus 0 cubed. In other words, 2 over 1. In other words, 2. Finally, a2 is going to be equal to 1/2 f double prime of 0, which is 1/2 times 6 over 1 minus 0 to the fourth power. 1 minus 0 to the fourth is just 1. 1/2 times 6 gives me 3. The first three coefficients are just 1, 2, and 3. The answer to this question is B. Assuming you had these Taylor series coefficients memorized coming into the test, you're done at this point and you're moving on. What if you didn't have these Taylor series coefficients memorized? No problem. You can derive them pretty easily. The idea with these Taylor series coefficients is you want to build this polynomial out here. I guess really it's a power series, an infinite polynomial. that's equal to this function inside the radius of convergence. How are you going to make these two things equal? Well, the first thing is you should make sure that they're equal to each other at the point where this thing is centered. Again, we're centered at 0. So what that means is we have to make sure that p of 0 is equal to f of 0. What is p of 0? We'll change all the x's into zeros, and all that would be left is this first coefficient, a0. So a0 is always just going to be equal to f of 0. Okay, cool, but what about a1 and a2? Well, we figured out a0 by making sure this polynomial and this function were equal to each other at 0. The next thing we want to do is make sure that this polynomial and this function have the same derivative at 0. So we got to take p prime of 0 and set that equal to f prime of 0. What's p prime of 0? Well, this constant goes away, this x goes away, and then for all these remaining terms, I'm going to have to bring the power down in front, but I'm still going to have an x left in each term. And since I'm evaluating the derivative at 0, any terms that have an x left in them are going to go away. What I'm saying is p prime of 0 is just going to be equal to a1. In case you struggle to see that, let me write p prime of x over here. Again, a0 goes away. The derivative of a1x is just a1. The derivative of a2x squared is 2a2x. The derivative of a3x cubed is 3a3x squared, and so on. If this is p prime of x, when I evaluate p prime of 0, all these terms are gone, and I'm left with just a1. What I'm saying is a1 is just going to be equal to f prime of 0 like we have written over here. For a0, we made sure that the polynomial and the function were equal to each other at 0. For a1, we made sure that the first derivative of the polynomial and the first derivative of the function were equal at 0. For a2, you can probably guess, we're going to make sure that the second derivative of the polynomial is equal to the second derivative of the function evaluated at 0. What's the second derivative of the polynomial? Well, I got the first derivative right here, so I can figure out the second derivative pretty easily. This is just a constant, so it goes away. When I take the derivative of this term, I'm left with 2a2. When I take the derivative of this term, I'm left with 6a3x. If I took the derivative of the next term, which would have been 4a4x cubed, I'd get 12a4x squared, and so on. But I don't want p double prime of x, I want p double prime of 0, so I change all the x's into zeros, and again, all these terms go away. All that I'm left with is this first term, which is 2a2. But I don't want 2a2, I just want a2. So what I do is divide both sides of this equation by 2, and I get this formula, a2 equals 1/2 f double prime of 0. During the pressure of a test, you probably don't want to derive all these different coefficients, but it might make it a lot easier to memorize these formulas if you kind of understand where they come from. So that's what I'm kind of attempting to do here. Once we solve this equation for a2, we have the formulas for our first three coefficients, and all we got to do are plug in the numbers like we saw down here. If you're still watching this video, I want to reward you with a completely different way you can do this problem, a really cool way to do this problem. If you think back to the second problem on this test, maybe you remember that I listed a whole bunch of common Taylor series here. And if you stare at this list, unfortunately, you don't see one for 1 over 1 minus x squared. But you do see one that's really close, 1 over 1 minus x. The expansion for this function is just 1 plus x squared plus x cubed, and so on. Turns out we can use this Taylor series expansion to figure out the expansion of this function, 1 over 1 minus x squared. To do so, you have to be a little bit clever. You have to recognize that the derivative of this function is exactly 1 over 1 minus x squared. The derivative of 1 over 1 minus x is the derivative of 1 minus x to the negative 1 power. Using the power rule, I bring the negative 1 down in front. I subtract 1 from my exponent to get 1 minus x to the negative 2. But then I'm not done because of the chain rule. I have to take the derivative of this inside function, which gives me another negative 1. This negative 1 and this negative 1 cancel out, and I'm left with just 1 minus x to the negative 2 power. In other words, 1 over 1 minus x squared. That ends up being really useful because if this is equal to this, then the derivative of this is going to be equal to the derivative of this. If I take the derivative of the left-hand side, as I showed over here, I get 1 over 1 minus x squared. If I take the derivative of the right side, this goes away. This x turns into a 1. This x squared turns into 2x. This x cubed turns into 3x squared. The x to the fourth that I didn't bother to write turns into 4x cubed. Maybe you can see the pattern. What I'd be left with, I could write as the sum from n equals 0 to infinity, almost of x to the n, right? Here's the 1, here's the x squared, the x cubed, all those line up. The only difference is when n is equal to 1, for example, I have a 2 out in front. And when n is equal to 2, I have a 3 out in front. And when n is equal to 3, I have a 4 out in front. What I'm saying is I always have an n plus 1 out in front. But we don't even need the general form of this. We had our answer all the way back at, this step, I guess. This question is only asking us for the first 3 coefficients. They're 1, 2, and 3, as you can see here. The answer is B without doing any of this work. I think that's pretty cool. So again, to recap, probably the most straightforward way to answer this question is to just know these formulas for the Taylor series coefficients. If you don't know these formulas, or if you need help memorizing these formulas, think about their derivations that I showed over here. Once you have these formulas, it's as easy as calculating a couple derivatives and plugging in a few numbers, and you're done. However, as is often the case on this test, if you're really clever, you can save yourself a little bit of time. This isn't hard, but it is a little bit tedious, right? It would take a minute or so. If you happen to have memorized the common Taylor series expansions that I talked about in problem 2, and you happen to be able to recognize that the derivative of one of those is the function in question, then you could derive the expansion of this function here. That's pretty neat. I guess a third and final option would just be to add this function to your list of common Taylor series expansions. I probably wouldn't do that because that's just more and more memorization that I'm asking you to do. And what are the odds that this exact function shows up on your test? I think thinking about how you can use some that you already have memorized to come up with some new ones might be more useful to you.